Welcome to today's Explainer. We're tackling one of the most persistent, yet completely hidden traps in machine learning. We're going to break down 5 absolutely essential ML model accuracy metrics. But more importantly, we're talking about what they are actually good for in practice. Because look, if you work with data, you already know that judging a model's performance just isn't as simple as asking, hey, is it accurate? We really need to look much closer than that. Okay, let's dive right in by posing a pretty fascinating paradox. How is it possible that 2 models can post the exact same average error, look absolutely identical on a spreadsheet, but then behave completely differently when you actually deploy them in the real world? It happens all the time, and honestly, it often leads to catastrophic business decisions. The secret is simply understanding that not all errors are created equal, and today we're looking at 5 specific metrics that give us the exact conceptual tool belt we need to figure out why.
Section 1. The 5 metrics. Predicting a number? Not a category. And hey, there's Techie from AI Tech Hub, bringing us our conceptual tool belt.
Before we pull out the very first tool, keep one absolutely crucial point in mind. These are regression metrics. That means they're used when your model is trying to predict a specific number, like a price or maybe a temperature, not a category like spam or not spam. So let's start with the most straightforward tool in the belt, MAE, or mean absolute error. The math here is beautifully simple. You just take every single prediction's error, you completely ignore whether the guess was too high or too low, and you just average them all out. The result you get is literally the average size of a typical mistake. Plus, it's presented in the exact same units as whatever you're trying to predict. So if you're predicting dollars, your MAE is in dollars.
The core utility of MAE really comes down to that simplicity. It gives you this highly intuitive read on just how far off are we, usually. If you want a really straightforward baseline where every single error counts equally, meaning a $10 miss is exactly 10 times worse than a $1 miss, MAE is absolutely your go-to.
But here's the thing, sometimes all errors shouldn't be treated equally. Enter our second tool, RMSE, or root mean squared error. It's a very similar idea to MAE, but with a major mathematical twist. Every individual error actually gets squared before you average them, and then you take the square root of that whole average right at the very end. So why do this? Because squaring the errors fundamentally changes the math. It forces the big errors to count disproportionately more than the small ones. It actively punishes those large misses.
And that makes RMSE totally perfect for situations where a few huge misses are far more dangerous to your business than a bunch of tiny incremental ones. If a single outlier mistake could entirely blow your budget or sink a project, RMSE acts as your built-in alarm bell. It's going to ring loud and clear to warn you about those potential catastrophic failures.
Next up is R-squared, which is also known as the coefficient of determination. We're shifting gears entirely here. R-squared asks a completely different question. It doesn't even look at direct error in units. Rather, it looks at variance. It actually measures what fraction of the actual variation in your outcome your model manages to explain, placing it neatly on a scale from 0 to 1.
So, what is this actually good for? Well, it's genuinely amazing for a quick, single-number sense of overall model quality. If you happen to have 2 different models attempting to solve the exact same problem on the exact same dataset, R-squared gives you this fantastic comparative snapshot to tell you which model is capturing the underlying trends better.
Let's keep moving. Next is MAPE, or mean absolute percentage error. Instead of giving you an error in raw numbers like dollars or pounds, it expresses the average mistake as a percentage of the actual value. It takes that raw error and converts it, completely normalizing the scale of your mistakes.
Now, that normalization is incredibly key when you're comparing accuracy across wildly different scales. Just think about it. A model predicting the price of $10 retail items and a model predicting the value of $10 million corporate deals. You simply cannot compare them fairly using raw mathematical error. The millions will completely wash out the tens. But a percentage error? That puts them on an even playing field, so you can actually judge their relative predictive power.
Our final metric in the tool belt is within tolerance accuracy. This one steps completely away from pure averages. Instead, it asks what percentage of your predictions land within some meaningful, predefined threshold of the actual value. So for example, you might ask, hey, how often is our prediction within 20% of the actual target?
The real beauty of this metric is its real-world application. It's genuinely good for communicating results to people who aren't statisticians. When you're presenting to stakeholders, executives, or maybe a sales team, within tolerance acts as the ultimate business-friendly translation tool. It just answers that simple human question: how often are we close enough to be genuinely useful?
Section 2. Real example.
predicting home sale prices. Let's actually see why picking the right metric from that tool belt matters so much.
Imagine we're evaluating two different hypothetical models for a real estate firm. Model A is consistently just a little bit off on every single house it looks at. It's never wildly wrong, just slightly imprecise across the board. Then we have Model B. Model B is spot on, practically perfectly predicting almost every standard house, but it gets badly, wildly wrong on one unusual, highly expensive property. Let's see how our metrics handle this showdown.
Notice the totally conflicting reactions from our metrics. MAE might report these two models as being roughly similar, because it treats every error proportionally the same, completely regardless of size. It effectively hides Model B's catastrophic failure. RMSE, however, tells a totally different story. Because its math squares the errors before averaging, Model B's massive miss gets punished disproportionately hard. That leads RMSE to crown Model A as the safer bet, even though Model B was actually more accurate on almost every individual house.
And what about the rest of our tool belt in this scenario? Well, R² would give the firm a sense of overall fit across the entire data set of houses. MAPE becomes absolutely essential the moment the firm wants to compare the accuracy of this home price model against, say, an entirely different asset class like commercial buildings. And that within tolerance accuracy, that's what you actually take to the real estate agents to show them exactly how often the algorithm is close enough to use in a live client negotiation. So the absolutely crucial point here is this. No single one of these metrics is the right one. If you only pick MAE, you could easily deploy a model that occasionally fails catastrophically without you knowing. If you only pick RMSE, you might become way too cautious about rare, large errors that honestly maybe don't even matter for your specific use case. The real skill isn't memorizing formulas. It's knowing exactly which question you're trying to answer and picking the specific metric built to answer it.
Techie is back one last time to help us rapidly synthesize this. 5 metrics, 5 distinct questions. You use MAE for the simple average size of a typical mistake. You use RMSE when big misses are incredibly costly and need to be punished harder. R² is your lens for overall model fit. MAPE is essential for comparing accuracy across totally different scales. And within tolerance accuracy provides a highly practical, business-friendly read on real-world usefulness.
That pretty much wraps up our deep dive into regression metrics. But remember, regression is strictly for predicting numbers. If you're predicting categories, like spam or not spam, you're going to need classification metrics. And we actually already have that side covered too. We dive into concepts like precision, recall, and F1, which explain performance at a specific threshold, plus ROC-AUC, which shows the trade-off across all thresholds. If you want to dive into those, just drop a comment with the word classify below, and we'll link you right to that explainer.
I'm going to leave you with this final thought for your very next project. Take a really hard look at the tools you're using. Are you picking your regression metric purely out of habit, just because it happens to be the default in your software? Or are you actively choosing it because it actually answers your underlying business question? The difference between those two approaches might literally dictate the success or failure of your entire model. Thanks so much for joining me on this explainer. Keep asking the right questions, and I'll see you next time.